Hello students, in our previous classes we have seen that for a multi-degree of freedom systems case what we can do is we can consider that our displacement vector is composed of superposition of all available mode shapes, and we also have seen that we can use those mode shapes. We can formulate a matrix which is a mode shape matrix, and that mode shape matrix can be used to diagonalize mass matrix and stiffness matrix, and then we kind of transform our set of equations which are in the coordinate system that we have written initially, where system was coupled, and we can transform them in our modal space, and in that case we get decoupled equations, right? So we have done this before for 2 degree of freedom system. We have found out mode shapes of that, and in order to find out mode shapes we considered mass matrix and stiffness matrix. So undamped case is something that we have seen, and considering that undamped undamped and homogeneous case, we found out mode shapes and natural frequencies, and whatever mode shapes we have found out for that undamped and a homogeneous case, we use the same mode shapes to arrive at displacement solution for that case where there was certain forcing acting onto the system. However, in that case also there was no any damping that we have considered before. Now we are going to see what happens if damping is there in the system. Okay, so let's consider the same system that we have talked about. Okay, in earlier case we considered that this is mass number 1 and this is mass number 2, and block mass this m1 and m2, both these blocks have got identical masses, and we also have assumed that stiffnesses of all these springs are identical. In that case we ended up with mass matrix which was like m00m, and the stiffness matrix that we have obtained was like 2k minus k and 2k, right? And what we have done is we have analyzed this system initially for no any external forcing, and in that case we have obtained natural frequencies of the system, and we also have two mode shapes, and first mode shape was like this 1 1, and the other mode shape was 1 minus 1. Now thereafter what we have also done in the last class is that we normalize these mode shapes with mass matrix. Okay, so we considered mass normalized mode shapes. So what is that mass normalized mode shapes? Let's say if you multiply by 1 1 and let this be m00m, this is 1 1 transpose, that is a transpose of the first mode shape. Okay, and then you have first mode shape over here, then that gives you 2m. Okay, so what we have done is we multiplied by 1 over square root of 2m to this mode shape 1 1 1. So rather than taking 1 1 as the mode shape, if you take this as the mode shape, which is 1 over square root of 2m into 1 1, then what you get is 1 over square root of 2m, this one, okay, comes out to be like this. That is u transpose u1 transpose mu1 is something that we are finding out. Okay, so if we find out that, then here you have 1 over square root of 2m, and then that comes out to be equal to 1. Okay, so this is what is the mass normalized mode shape, that is the modal mass comes out to be equal to unity. Okay, so if you decompose our matrix, okay, so if you do this, that is u transpose m u, where all vectors in this u matrix, they are mass normalized. In that case you get this system as identity matrix, right? So your final equation will be like this: identity matrix times eta double dot plus, here you will be having diagonal matrix where diagonal values will be equal to omega z, that it will be the zth natural frequency, so I'll be calling it as omega nz square. Okay, so this will be the diagonal value, and all of diagonal values will be 0. Okay, so it will be a diagonal matrix, and here you have n that is equal to 0 when there is no any forcing. If there is any forcing, then you get a force vector over here. Okay, that force vector is nothing but this u transpose applied onto force vector which was acting over here. Okay, So this is something that we have seen, and we have seen that this matrix, which is identity matrix, is a diagonal matrix. This is also a diagonal matrix, which is U transpose KU. Okay, and diagonal terms comes out to be equal to omega nj square if you are considering mass normalized mode shapes. Okay, so when mode shapes are mass normalized, in that case stiffness matrix comes out to be like this, and mass matrix is R. Okay, this is only for those systems which don't have damping included into it. Now let's consider a case when there is a damping. Okay, and damping can need not be distributed in the same fashion as you have the stiffness terms distributed, right? So you have K over here, K over here, and K over here. But in the damping case, you can have C here, then there can be 2C here, and then there can be 3C, or anything can be over here, right? So you are as of now unaware of that this one. Okay, what is it that is sitting over here? So in that case, you will be able to appreciate that this U transpose CU, that will not always be diagonal. Okay, that will not always be a diagonal matrix. In certain cases it may turn out to be diagonal, but in most of the cases you would see that it doesn't turn out to be diagonal. So for those cases which this matrix also turn out to be diagonal, then your life becomes very easy. So in that case, what you have to do is, so initially assume that you have found out natural frequencies and mode shapes without considering C. Okay, the way we have been doing it even for single degree of freedom system. So in order to find out natural frequency, we don't consider damping, right? So damping is something which is not considered while deriving natural frequency. Okay, however, while finding out damped natural frequency, we considered damping. But what is the natural frequency if I ask you, then what you'll be doing is you'll be considering only mass and stiffness, right? Similarly over here, in order to solve initial eigenvalue problem, we'll be considering only mass matrix and stiffness matrix, and damping matrix will not be considered while deriving mode shapes and eigenvalues. Okay, this is how we generally do. Okay, you can also use this matrix and then find out corresponding damped mode shapes, but that procedure becomes really trickier. It's not easy. In that case, what you will be doing is you will be solving this equation, that mx double m, which is this mass matrix, times this acceleration vector plus this c times this displacement vector plus k times x equal to 0. Okay, so this is the set of equations that you will have to solve. Okay, and finding out damped mode shapes at times can be really very tough job. So we are not going to talk about that in this particular course. Okay, so let's assume that what we are doing is we are finding out mode shapes for undamped case. Okay, and we are proceeding in the same way as we have done before. Okay, so let's say that you have found out U, which is a vector of which is a matrix of all mode shape vectors. So you have u1 and u2 over here. Okay, so the first column is u1, second column is u2. So first column is first mode shape, second column is second mode shape. This is a mode shape vector, mode shape matrix that you have generated. Okay, and while deriving this, you haven't considered C. Okay, so without considering this term, you have obtained this mode shape matrix. Okay, now while deriving solution of force vibration response, that time you are going to consider this C. Okay, so now force vibration, in that force vibration case, what is the equation of motion, set of equations of motion? Then that case you get this one, right? Here you will be having F vector. Okay, so the same stuff, but with only this term added. Okay, this is the only additional term, okay, which was not there earlier. Now what we are going to do is we are going to consider that even in this case, when there is a damping, then solution of this damped system under this externally applied force system F can still be approximated as a superposition of mode shapes that you have obtained for that system which was not having any damping into it. Okay, so I'll be assuming that this is how I can still write. Okay, So this is an assumption, this is an approximation. Okay, so this in this light of more than approximation, this is an assumption. So in this light of assumption, we are going to find out what is x. Okay, if I can write it down in this way, then what comes out to be equal to this eta 1 and eta 2. Okay, so which essentially means that I am writing down x as superposition of this modes, and this is what it is, right? So it is U matrix and this is eta vector. It's the same stuff that is written over here, arranged in a matrix form. Okay, so this is solution of damped MDOF system which is under forced or externally excitation, which is kind of experiencing. It is a displacement solution for that kind of condition, and this is this force vibration response of the damped MDOF, this one. Okay. And this thing, not etas, but these u's that you are writing over here, which you are superposing to find out this x, those u's are mode shapes or eigenvectors, okay, of corresponding undamped MDOF system. Okay, so same MDOF system, by putting C off, you have to find out what is going to be this U matrix. Okay, so find out this U matrix and assume that you can use still the same U to generate this X. Okay, and how are you going to find out X from these U's? You are going to superpose those U's. Okay, so U1, U2 that you have obtained, you will be superposing them by giving weight eta 1 and eta 2. Eta 1 and eta 2 are time dependent. Okay, so as time changes, value of eta 1 and eta 2 is going to change, and that is what is going to be the variation of eta 1 with respect to time and variation of eta 2 with respect to time. Okay, so that is something that now we are interested in finding out. So what is the variation of eta 1 and what is the variation of eta 2? Okay, so we want to find out this eta 1 and eta 2. Okay, so what we'll be doing is we'll be putting this expression the way we have done before in our equation of motion. So we'll be writing down this one, m times u times eta plus C matrix is this, then u, here you will be having eta double dot, and here you will have eta dot, which is first order derivative of eta with respect to time. Then you have k, u and eta here, and here you have f. Okay, now we know that this u's behavior is such that u transpose mu is equal to I. We have picked u's in such a way that it comes out to be equal to I. Okay, so those are mass normalized u's. Okay, and u transpose k u comes out to be equal to omega r square, diagonal term. Okay, so this is what we have so far seen. However, as I just now said, that the C matrix need not always satisfy this condition, that U transpose CU need not always be a diagonal matrix. Okay, so this D is a diagonal matrix. It need not always be diagonal matrix. Okay, it can still have off diagonal terms, non-zero. Okay, so if off diagonal terms are non-zero in this D matrix, then the whole idea of going for this, okay, in which we obtained in earlier case two different single degree of freedom systems, that is two different equations which are not coupled to each other, so that won't at all get satisfied, right? Because even if I pre-multiply by U transpose to this entire system, this will be diagonalized. Okay, this will be diagonalized, that is also okay, fine, but this system is still not diagonalized, and it has still got some off diagonal terms, which essentially means that two equations that we'll be getting from that are still coupled. Okay, so we cannot obviously solve those two equations separately, considering those two are two separate single degree of freedom systems. So what we do in that case? So there is one workaround, okay, that all need not always work once again, but in most of the cases it works, and that is one of the easiest way in which you can tackle such kind of damped multi-degree of freedom systems. Okay, so what is that way? That is called as a Rayleigh damping or a proportional damping, in which what you do is you approximate this C as a linear combination of mass matrix and stiffness matrix. So you write down this as alpha times m plus beta times k. Okay, so this is what you are saying. Okay, so now your job is to find out what is appropriate value of alpha and beta. Okay, and if you are able to do that, then obviously you will be able to replace this c by this combination. Okay, so what we'll be doing is we'll not be writing down c in this equation, but we'll be writing down alpha times m plus beta times k. So what will happen is that, so I'll get such kind of a system. I'm pre-multiplying by u transpose m u, this eta double dot. Now I will have alpha times u transpose m u plus beta times u transpose k u, multiplying vector is this eta dot plus u transpose k u eta, that comes out to be equal to f tilde vector, right? So this is what we have obtained, so which essentially means that this is I eta double dot plus this will be alpha times I plus beta times omega r square. I'm writing it in this way, which symbolizes that it is a diagonal matrix. Eta dot plus this will be omega, again I'll be writing it in the same fashion, eta, that is equal to f tilde. Okay, so in our case, when we have 2 degree of freedom system, then I'll be writing down it in this way. I'll write down individual equation, n1 or eta 1 double dot plus alpha plus beta times omega n1, this is omega nr, this is omega nr, okay, omega n1 square times eta 1 dot plus omega n1 square eta is equal to f tilde. Okay, and eta 2 double dot plus alpha plus beta times omega n2 square eta 2 dot plus omega n2 square eta 2 is equal to here it will be f1 tilde, here it will be f2 tilde. Okay, this is equation number 1 and this is equation number 2. So in our case, we are going to get these two equations. Okay, so since we have 2 degree of freedom system, so if you have, let's say, 3 or 4 degree of freedom system, then you are going to get such 3 or 4 equations. So depending on how many number of degrees of freedom are there, you are going to get those many number of degrees of freedom or those many number of equations. Okay, so because you have those many number of mode shapes. Okay, now you can see that this equation is same equation that we have considered in case of damped behavior of single degree of freedom system. So damped SDOF systems behavior. So we wrote down in that case x double dot plus 2 xi omega n x dot plus omega n square x equal to f. Right, we have done this before. So we our initial system, which was mx double dot plus cx dot plus kx equal to f, so it will be f bar. Okay, so if we divide by m, so c by m comes out to be equal to 2 xi omega n, because c itself is 2 m xi omega n or 2 xi m omega n, and this k by m comes out to be equal to omega n square. So if you see correspondence between this equation that we have studied before and whatever equations that we have just now obtained, then you will be able to see that this bracket, which is getting multiplied by this n r double n r dot, okay, so first derivative of eta, not n, eta, then you will be able to see that alpha times beta omega r omega n r square, that is equal to, that is this term, okay, so this term is equal to 2 xi omega n r, right? So compare this with this one, okay. So in our case, when we have 2 degrees of freedom systems, then we'll be saying that alpha times beta times omega n1 square is equal to 2 xi, I'll be calling it as xi1 omega n1, okay, and alpha times beta times omega n2 square, that is equal to 2 xi2 omega n2. So from this equation I can write down that xi1 is equal to alpha plus beta omega n1 square divided by omega n1, and xi2 value of that comes out to be equal to alpha plus beta omega n2 square divided by omega n2. Now what is this xi1 and xi2? So you can correlate it, okay, with this equation, and you will be able to see what is this eta 1 representing. Eta 1 is representing contribution of mode number 1, okay. So we said that whatever is pre-multiplying over here, we'll be calling it as a modal mass, right? So this term is modal mass, this term we said is modal stiffness. So obviously this term has to represent modal damping, okay. So this entire stuff, that is alpha plus beta times omega nr square, represents modal damping, which is equal to 2 xi r omega nr, okay. And what is modal damping ratio? That is equal to xi r, right? So what is the damping ratio of first mode shape? That is first modal damping ratio, that will be equal to, in our case, that will be equal to this one, right? This is first modal damping ratio, this is second modal damping ratio. So how much amount of damping is there in first mode is this one, and how much amount of damping is there in second mode is this one, right? So this is what is the modal damping ratio. Now I'll expand it even further. I'll write it down this way. Xi1 will come out to be equal to alpha divided by omega n1 plus beta divided by beta times omega n1. Here it should be omega n1, right? Alpha is proportionality constant of mass matrix, beta is proportionality constant of stiffness matrix. That is, in C, how much of M is there, that is taken care of by alpha, and how much of K is contributing in C, that is taken care of by this term beta, okay. So now what is happening is that if alpha is large, okay, if alpha is large, then what is going to happen? This term is going to be larger, right? So this term being much larger, what is the meaning of that? What is the implication of that? That for smaller natural frequencies, that is for, let's say, mode first mode, okay, damping will be much larger, whereas for higher modes damping will go on reducing. This is the implication of having high alpha, okay. So let's assume that in a typical case you put beta equal to 0, okay. So this term won't take part, right? So only this term will be there, and this is what is going to be xi in that case, okay. So if you say that C is entirely written in terms of M and not in terms of K, okay, so in that case this is obviously an extremity, we have weighted combination, but in that extremity, so what happens is that damping of the first mode shape or that comes out to be very small rather than damping of second mode shape. This generally doesn't happen for those forces which are having smaller frequencies. So for smaller frequency forces which we typically encounter, so for in those cases we never go for larger values of alpha and smaller values of beta. However, we go for much larger value of beta, which ensures that xi increases with increasing value of omega nr. Okay, so for larger frequencies, you are going to get larger xi, that is larger damping, that is larger mode shapes are more damped. Okay, so those are not going to play a bigger role, bigger picture in final response than smaller mode shapes, right? So smaller frequency details, those are going to have their footprints in your final response if you put beta to be larger and alpha to be smaller. Okay, so this is what we do for, so beta larger and alpha smaller is preferred one when you have smaller frequency forces. Okay, so forces which are having considerably small frequencies. However, if you have considerably large frequencies, then you can think of having beta to be smaller and alpha to be larger. Okay, so mass matrix will be governing C. Okay, so more contribution will come from mass matrix and less contribution will come from K matrix. Okay, so this is what is kind of a workaround to tackle C, and this is one of the easiest ways in which we can find out force vibration response of damped systems. Okay, so this it was much easier when we had 2 degree of freedom system. So let's consider a case when you have 3 degree of freedom system. So in that case, what you will do is you will obtain such 3 equations, right? So essentially it will be like this: alpha plus beta times omega n1 square, that will come out to be equal to 2 xi1 omega n1. Okay, then alpha plus beta omega n2 square will be equal to 2 xi2 omega n2, and third one will be alpha plus beta times omega n3 square, that will be equal to 2 xi3 omega n3. Okay. Now let's assume that you have picked values of alpha and beta. Okay, you know alpha and beta. Okay, so if you know alpha and beta, then you will be able to derive what is xi1, xi2 and xi3. Okay, it is not going to be a big deal in that case. Okay, but now let's assume that you are interested in fitting alpha and beta, or you are interested in finding alpha and beta. You want to pick alpha and beta. Then how do you pick that? So what we do is we initially assume how much amount of damping you want in first mode shape, how much amount of damping you want in second mode shape or third mode shape. But in this case you have only two unknowns, okay, which are values of which are to be determined. So you can give either how much amount of damping is is intended in mode number 1 and mode number 3, or mode number 1 and mode number 2, or mode number 2 and mode number 3. You cannot have this xi ratio specified for all mode shapes. You can specify it only for 2 mode shapes. You have to pick which 2 mode shapes you are going to consider, and accordingly you will be obtaining value of alpha and beta. So and then you will be using value of alpha and beta obtained to find out how much amount of damping is there in the remaining mode shape. So let's say you pick how much xi1 you want. Let's say I say that I want it to be equal to 0.1 and I want xi to be equal to 0.2, xi2 to be equal to 0.2. So xi1, if xi1 has to be equal to 0.1 and xi2 has to be equal to 0.2, then how much amount of alpha and beta I should use? Okay, so I'll be obtaining that, and once I obtain that, then I'll be finding out how much xi3 I am getting. Okay, so I'll be then checking, so am I gaining appropriate xi3, am I getting appropriate value of xi3? If I'm not, then I'll be changing this slightly, and again I'll be obtaining new alpha and beta, and I'll be saying whether I get that appropriate xi3. Okay, so that way you have to keep fitting these values. Okay, so this is what is in nutshell, or in a very brief manner, a discussion about how we tackle those systems which are multi-degree of freedom systems, which are damped in nature and which are experiencing externally applied forces. Okay, so we'll be stopping over here on this front, and with this we are concluding multi-degree of freedom system from the perspective of this course. It has been a very I would say, I won't say terse, but very, I mean, it was not that elaborate discussion, because we have a very stringent time limit this time. So this is all what we could consider for multi-degree of freedom system. So however, so you can build upon whatever that we have discussed based on that for other cases which are of interest but have not been considered so far in this particular course. Okay, and one more important point that I want to make over here is that whatever discussions that we have had for 2 degree of freedom system, those are applicable for any n number of degrees of freedom system. So in the same fashion, you can tackle any n number of degree of freedom system. Okay, so it can be 3, 4 or even 10 number of degrees of freedom in that system, but you can still tackle that system in a similar fashion that we have discussed. Okay, so in light of all this discussion, now I am stopping and we'll be concluding this 2 degree of freedom systems module. And in the next class we are going to rather start this thing continuous system. Okay, thank you so much.